Hello, my name is Tyler Reamer, and I will be going over the code review. So we're going to be starting at the top module, which encompasses all the other submodules that are used to develop and make the game GNOP. Starting at the top module, we have some basic inputs, such as the clock itself from the FPGA, the buttons right and left to move the paddle, a reset button, the difficulty button, which I titled A. Then we have the output for VSync and HSync for the VGA, as well as the RGB colors, and then also anodes and cathodes for the 7 segment. Here's where we initialize all of our wires and our registers that we're going to use later on. And then a simple modulus function that's going to be used for devising the time, just to have an easier 7 segment display, which I will go over later. We have multiple clock generators actually, but to begin with, this clock generator here is going to basically split up the clock into the top clock into the lower clock, and that lower clock is then used to run the entire VGA system. Here we have our VH sync generator, which we will talk more in depth about, but this uses that clock from the clock generator. Then we have a second clock, and this actually isn't a second counter as it says. This is a quarter of a second counter. It's been modified. Second 2 counter, this is the actual second counter. As you can see, second clock. This is the quarter second clock. This is the second clock. And then we have a display module, which I came up with in Lab 4, which can take in digits on an array from 1 to 8, and it displays whatever the binary value of this digit is, or whatever the value of this digit's input is, it converts it to binary, and then from binary into decimal and displays that on the 7 segment on the FPGA. It also splices the clock automatically and takes in anodes and cathodes to display that. So before we get into some of the logistical code behind the game, why don't we look at the 7 segment? So the 7 segment is composed of a module called display segment. Display segment takes in an input wire that is the clock, and it outputs onto anodes and cathodes in a wire. And then it also takes in 8 inputs, which are the digits that are represented on the 7 segment. This also needs to take in a refresh counter, a refresh clock, and the digits displayed. So the refresh counter, this is the refreshment rate of the 7 segment, which I believe is 10 kilohertz. And then the refresh clock is going to be used to cycle through those in the rotator, and that's how we know exactly which anode we're going to be pushing the cathode values onto. And then the digit displayed, this is where we store our value temporarily when inputting these digits. Okay. First module to cover is the rotator. The rotator takes in an input called refresh, which is the refresh clock rate, which again is 10 kilohertz, and it outputs a register number, which is called case number, and this just changes the value on the anode to the correct one. So as you can see, we start at anode 0, move to anode 1, 2, 3, 4, until we hit anode 7. And then at that time, we reset back to 0. And here's our refresh counter clock. This takes in a clock, and it outputs a value when it's starting with a 0, so starting low, when the clock is divided by a local parameter of 5999, or 4999, sorry about that. There's not much more to be said here. It just counts up to the value of 10 kilohertz and then it repeats it. So if you take the clock speed and divide by 5,000, you'll get 10 kilohertz. Well, actually, I think you get 20 kilohertz, and then it has a divider again where it divides it back into 10 kilohertz. Anode control, so this takes in the refresh counter number that we were talking about before, and based on the case of the refresh counter, we know what to put out, which anode we're pushing out to, and we use 8-bit hot, and that way we can determine which exact anode we're going to be pushing out onto. So next we'll be talking about cathodes. So the cathodes, basically this is what we're going to be using to display the value onto the anode. This is synced into the anode controller. So when the anode controller is on the right anode, the cathode controller is also running in the background to compute and know which digit is going to be being displayed. So we take in these 8 digits. Again, these represent the 8 anodes. And each of these values then gets converted into the proper digit displayed, and again, using the refresh counter. So depending on which anode we are on, we take in a case. So if we are on anode 0, we take in digit 1. If we're on anode 1, we take in digit 2, again and again and again, so forth. And then this is where we actually convert those values on the digit displayed into a number. And so here we have 0 through 9, and these all represent the actual values 0 through 9. Here we have 10, which means it's blank, doesn't display anything. 11 is a P, 12 is an N, and 13 is a G. And then the default cathode is a 0. And so that covers the display segment. And as you can see here, we just take and wire it together, hook it all up together. And that way we can input these simple digits and then just output onto anodes and take in the input of the clock. And that gives us our 7-segment display. Relatively simple. Moving on to the clock generator. The clock generator is taking in a frequency of 100 millihertz, or 100 million hertz, and we are trying to divide that. And this is just a very simple clock generator that I found online. This clock generator just takes a counter, takes in a divisor frequency. The divisor then is set to a certain parameter, which is what we're going to use to divide the clock by. Every time the clock of 100 megahertz, we count until we reach the divisor -1. So we're going to count up to 3. And every time we count 3, we're going to output that. And then depending on whether or not the counter is less than that divisor will depend as whether or not we put out a power signal or not. So kind of what this represents is we're cycling between 0, 1, 2, and 3. And then every time we hit 4, we're going to reset back to 0. And we're also going to output a signal since it is not less than the divisor result divided by 2, since it is not 2. Okay, and then we have the VH sync generator. This is sort of code that I happened to stumble across while doing the project, and for some reason I'm having a very odd bug that causes it to generate a 720 by 480 image, and I still don't know how to quite figure that out or fix that, so I don't fully understand this. But basically it takes in a clock, outputs the VH signal as well if it's in the display, and then where it's currently at, counter X and counter Y. This just counts. Right here is representing 1/5 of a second. If this was a 9, that'd be representing this is representing 1/50th of a second. If this was 2 9s, it would represent, instead of the 0, that would represent 1 second. And this is representing an actual second, as you can see. And then top module, we're going to talk about a little bit how the game code works. So we're going to have an X and a Y representation of the location on the graph for the ball, as well as the ball's current position. So that's starting from its origin point, not its other points. Difficulty rating, this is going to be used to determine the size of the paddle, and then the paddle position, which is going to be used to determine where the paddle is at. This is just how you move the paddle position, left or right, pretty simple. This is how you determine the size of the ball, actually. These parameters determine as to whether or not the ball's dimension. So the ball is going to be 16 by 16. And we're going to have a wire called ball, which is just going to tell us where the origin position is in respect to where the ball is. And then we are going to also have the paddle right here, paddle definition. This is the border definition. So this is how you know if you're touching the border or not. And then if you ever conflict with something, that's going to be a paddle or a border. And we need to know that from when we write our collisions. Speaking of collisions, here they are. So our collisions are actually relatively simple. So the collision means that we're interacting with some sort of an object, such as a conflicting thing, the border or the paddle, at the ball's relative position. So here we're going to have the VGA demonstration for the game GNOP, and I'm going to start off with the FPGA physical switches, buttons, and 7-segment, and then we will move to what is actually being displayed currently on the VGA. As you can see, the 7-segment is incrementing by 2 per second. This is a bug. This is not the actual implementation currently. I'm not quite sure how to fix it because I have a proper clock speed going into this. It's just incrementing at the incorrect rate.
we can also see that the game is being displayed here, GNOP, GNOP. And we're going to talk about two things currently. So these three switches here are used to change the difficulty based on their correlative value in binary. This representing 1 and this representing 7. 7 being the hardest and 0, standard, being the easiest. The left button here will move the paddle left. The right button here will move the paddle right. This upper button here will be used as a reset button, and that will reset the game. Firstly, I want to demonstrate the difficulty changes. If you watch the paddle here and we increment to difficulty 1, you'll notice that the paddle has now shrunk. If I decrement from difficulty 1 back to standard and then increment from difficulty 1 or difficulty 0 or standard to difficulty 2, you'll notice that changes as well. Difficulty 4 with a max difficulty of difficulty 1, being smaller than the ball itself. As you can see, when I push the right button, the paddle moves right. As I push the button to go left, it moves left. Demonstration, moving right. On the left button, moving left. Now I want to demonstrate some of the collision blocks. So as you can see, the ball is just bouncing around the screen, doing its thing. And here's one of the first bugs that I want to talk about. The screen itself is displaying a 720 by 480 image for some reason. I'm not quite sure how to fix that, and I don't know anybody else who's gotten the same error. I'd also like to demonstrate, as you can see, these collisions are occurring on the border, as well as going to be occurring on the paddle. And this is because I made special parameters inside of the code that adjusts for these collision blocks. The code that was used to reference and design this game can also be found online, and the resource will be left inside of the final project link.